Hello guys, welcome back to my channel Gamma Digamma. So someone recommended an integral to me in the comment section of the last video, and I am here with that same purpose to do that integral. But the thing is, it's a hard integral, and I need to get a result before doing that integral. So let's consider we can treat this video independent of any other video. Say I of p comma q is defined as integral from 0 to 1 x to the p, the fractional part of 1 over x to the q dx. Well, what we can do here starting off is sort of ease out the expression inside the fractional part. So by that I mean just use the substitution y equals 1 over x. That means dx is negative 1 over y squared dy, and our bounds of integration go from 1 to infinity now. We have y to the minus p and a minus 2 because of the differential element, y to the q dy, of course in the fractional part. Now what we can do is we can employ the same trick we use when we have fractional parts. We sort of split the integral over from 1 to infinity into these integer chunks going from k to k plus 1, and then we sum from k equals 1 to infinity. And by doing that, by linearity, you're going to add up each individual integral segment by the sum, and then you're going to get 1 to infinity, just broken up into integer parts, like one integral from 1 to 2, 2 to 3, and so on. Okay, so we have y to the p minus 2. The integer part is just y minus the floor function of y to the q dy. Now the advantage of splitting it up into these integer chunks is that the floor of y on any given segment of k to k plus 1 will always be k. That just follows from the basic properties of the floor function on sort of a subrange. Y minus k to the q dy. Now what we should do is we should define, and I shall use a different color here, we should define this integral as j pq k. And the problem is now sort of subletted into solving or finding the value of j p comma k. So j p comma k, what we can do is we can use integration by parts. So integration by parts is I'm going to integrate the first term because that's the easiest to integrate, and I shall differentiate this term. So we have minus y to the minus p minus 1 over p plus 1, y minus k to the q evaluated from k plus 1 k plus q over p plus q integral k plus 1 y to the minus p minus 1 y minus k q minus 1 dy. I was running out of space a little bit in that part. Maybe I can move it over there. Perfect. Now what we can do is we can simplify this. So evaluate the first term. So we get, after evaluation, k plus 1 to the p plus 1, because at k the y minus k term goes to 0. And then we have the second term becomes q over p plus 1, and you can check that the integral is just jp minus 1 q minus 1 k. So what we have here basically is we have, let's multiply p plus 1 on both sides. P plus 1 j pqk equals minus 1 over k plus 1 to the p plus 1 q times jp minus 1 q minus 1 k. What we have here is a recursive series, a recursive formula. The best thing we can do with the recursive formula is try to sum over and find like sort of a telescoping series, and then we can sort of individually find j p q k, which is basically the object we need here. The only problem is the state in which this expression is right now. It's not really telescoping. Look at the corresponding j values. So this prefactor is p plus 1 and q. So there's like a big difference between them. It's not like we have a p plus 1 here and we have a p here. So we have to address that difference. One really smart way of doing that is multiplying by p factorial and q factorial. That will sort of introduce as a product those other terms that are between p plus 1 and q. So let me just write that down. So what I want to do is I want to multiply by p factorial over q factorial. Okay, so when I do that, I now have p factorial times p plus 1 is p plus 1 factorial over q factorial jpqk equals minus p factorial over q factorial k plus 1 to the p plus 1, plus we have now p factorial over q minus 1 factorial j p minus 1 q minus 1 k. Now you see we can start to see a telescoping series, because we have p plus 1 factorial here, p factorial here, q factorial here, q minus 1 factorial here. So you see and even here like p and p minus 1, q and q minus 1. So you see there's that nice consecutive terms property. But the thing is, we have to introduce a variable for summation, because p and q are fixed values. So what we can do is introduce p minus q plus I plus 2 factorial instead of p plus 1 divided by I plus 1 factorial. So q is replaced with I plus 1 in general. J p minus q plus I plus 1 I plus 1k minus the consecutive term that we need, p minus q plus I plus 1 factorial over I factorial, and j p minus q plus ik equals negative p minus q plus I plus 1 factorial over I plus 1 factorial k plus 1 p minus q plus I plus 2. Okay, so what happens when I do that is when I is q minus 1, we get p plus 1. So when I is q minus 1, the term in the numerator just becomes p plus 1, and when I is 1, we basically get p minus q plus 3. And we need the q minus 1 term, the last term anyways. So what we can do is we can sum. So we can sum from I equals 1 to q minus 1. So when we do that, it's a telescoping series. So the last term survives. So the last term, this term will survive evaluated at q minus 1, and this term will survive evaluated at 1. You can check this out. We've done enough telescoping series in the past. So with that observation, we have p plus 1 factorial over q factorial jpqk equals p minus q plus 2 factorial j, and then we need to evaluate this when I is 1. So p minus q plus 1 k minus sum I equals 1 to q minus 1 of p minus q plus I plus 1 factorial over I plus 1 factorial, the k plus 1 term raised to the obnoxious factor that we have, p minus q plus I plus 2. It's a mouthful to say. Now what only is missing is that we have to sum from k equals 1 to infinity. Why? Because in the original integral, that's what we had, right? We found this value. We have to find the sum from k equals 1 to infinity, and that will give us IPQK, which is the value we need to find. Okay, so again, I'm going to change the color. So let's sum from 1 to infinity. P plus 1 factorial over q factorial IPQ equals p minus q plus 2 factorial IP minus q plus 1. So all that happened here was the j's changed to i's, because that's how we defined everything in the first place. Minus, there's going to be two sums, one from infinity and the one from 1 to q minus 1 of this term that I will not bother dictating. Okay, so far so good. Now the only thing that actually needs to be evaluated is this term here, because we need to find IPQK. So let's leave that alone. This sum will basically remain the same. We can't really do much about that. All we can look into is this integral. So let's do that. So let's do IP1, and then after we find the value, we can just plug p minus q plus 1 in place of this p here. So 0, 1, x to the p. That's what it equates to, the integral representation. Again, if we use the same substitution we did at the start, we get fractional part of y over y to the p plus 2 dy. And now using the integerizing the interval and the fractional part breaking up into y minus floor, and the floor becomes k because we split it up that way all that stuff. We get y to the p plus 2 dy. So now that if we split this up into two terms, we have y over y to the p plus 2, which becomes 1 over y to the p plus 1, which we can integrate. I'm going to skip some steps because otherwise this will be a long video. We integrate that, we get minus 1 over p y to the p from k to k plus 1. And the other term is the k over y to the p plus 2, which we can also integrate. We get minus k over p plus 1 y to the p plus 1, k plus 1k. And we can simplify this nicely. You can evaluate this completely to get 1 over p minus the Riemann zeta function. Maybe I'll do one more step because otherwise this will be a big jump. So 1 over p minus 1 over p plus 1 So what we're going to do is a p plus 1. What we're going to do is we're going to write this term as k. In the numerator we're going to add 1 and subtract 1. So when we add 1, we can separate that out. We get 1 over k plus 1 to the p, and then the 1 over k plus 1 to the p plus 1 term. So finally we get collectively sum from k equals 1 to infinity So this term in the brackets, in the first bracket, is telescoping series, so it goes to 1. You can check that. We get this term minus 1 over p plus 1, and in this term we see this is Riemann zeta minus 1, because the Riemann zeta start has the 1, but here we start with a 2 because k plus 1 will be a 2 for k equals 1. So we shall have the Riemann zeta of p plus 1 minus 1, and then that simplifies to and that's it, and that's all we need. So now what we got to do is we got to, instead of p, we got to plug in p minus q plus 1. That's all we got to do. And then when we go back, we can do another small change. We can do another small change when we look at this blue term. Not only are we going to plug in for this, we can also do a small change. We can change q minus I and call it j, and that affects this term here and this term here. That's all we're going to do. So finally we get p plus 1 factorial over q factorial IPQ p minus q plus 2 factorial over p minus q plus 1 minus p minus q plus 1 factorial zeta of p minus q plus 2 minus sum j equals 1 q minus 1 p minus j plus 1 factorial q minus j plus 1 factorial zeta of p minus j plus 2 minus 1. We can simplify this grand result nicely to get q factorial over p plus 1 factorial times p minus q factorial minus sum j equals 1 to q minus 1, or let's say I think it's q in the way because you can absorb some terms in p minus j plus 1 factorial q minus j plus 1 factorial zeta of p minus j plus 2 minus 1, and that's it. Yep, that's the grand result. This is equal to the integral xp fractional part 1 over x q dx. That's it. That's the big result. And I think I need to make, I think I forgot to mention is that in the main assumption in this is that these integers p and q, they have a strict relation. P is greater than or equal to q, and that's why we were able to write it this way. Sort of cover up the difference by multiplying by the factorial and then cancel it out by the telescoping series, is because p was greater than or equal to q, and this will hold. For other cases, it will not hold. As long as the condition is satisfied, it will hold. Now, I would like to discuss two special cases of this, which will be useful to us in the next video I'm going to make, because I'm going to directly take the results. So don't say I didn't prove it, because I will just refer you back to this video. Special cases. So I'm going to take this special case. And you can see this obeys the condition of p is greater than or equal to q, because n plus 1 is greater than or equal to n. So equals 1 half minus sum j equals 1 to n j plus 1 zeta j plus 2 1 over n plus 2 n plus 1, and the other one is INN. This is the saturating the inequality. This becomes 1 minus 1 over n plus 1. Sum j goes from n1 to n. Zeta of j plus 1. And there we go. That's a fairly safe place to conclude the video. Thanks for watching, guys. Please stay tuned for more content. The next video, the next integral where I'm going to use all these, is going to be freaking crazy. So please stay tuned for that. Peace out.